All right, class, we're going to take a look at basics of probability theory in this section, which is section 13.1. So an experiment is where we need to start, is an observation of random phenomena. And we have outcomes, and then all the possible outcomes are called the sample space. And then we're going to talk about some experiments here. But the difference between an experiment and there's just general theory probability that we'll talk about later. So we've got experimental probability, then theoretical probability. So we're going to start with some experimental, and so we select an iPad from the production line and determine whether or not it's effective. So this is just this is actually occurring. You're actually seeing it happen, so it's an experiment. So there's two different types of outcomes in the sample space. There's, well, you either have defective one or non-defective. So this is what you would actually type in the lab or click in the lab if you were looking for the sample space. So let's say we've got 3 children are born into a family, and then we note the birth order with respect to gender. And so you could have, I got the full picture here. So we've got the first child, it could be the boy or girl, and then the second child, if the first one's a boy, you could have boy, girl, and then from there you have branches. So this is the whole sample space drawn out pictorially. And basically, if you follow each line, I have boy, 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 or boy, boy, girl, or boy, girl, boy, and then so you can see it just working itself out. This is the whole sample space if you just follow your line down each one of these trees. All right, so let's take a look at rolling 2 dice. And we're looking at the pair of numbers shown on the top 2 faces. I've shown you a table before this table in the previous lesson, and it actually is the sample space. Notice my bracket at the beginning, bracket at the end. But basically, these are the different ways that you can roll the dice, 1 through 6, 1 through 6, and then you'd add all these up. And then later it'll help us to use this chart over here to show how many different ways there are to get a 12, how many different ways there are to get a 2, and these are actually the probabilities built into this table too, so let's put them in the next table. But anyway, this is the sample space for how you can roll a dice. Okay. Pair of dice, sorry. So write the event. Blue appears exactly once when we spin the given spinner 2 times as a set of outcomes, abbreviate red as R, blue as B, and yellow as Y. So, so here we're writing our set of outcomes. So we're looking for, just I need my marker. So just putting in my set the B in each grouping once. So we've got B, and then we spin twice, so the next one has to be R. Or it could be B, Y. And that's it. Because you can only have, you have to have blue, and then the next one would be R, or blue, then yellow. I guess if, it's order matter here. Because technically we could have got red, then blue, and then yellow, then blue. Yeah. So we probably do need those extra 2 orders because you're spinning it twice, and that's the way that it could actually have happened. So this is my overall sample space, and so the order does actually matter here for how you actually get your spinner to work, or spinner outcomes, sorry. Here we go. So each event as a set of outcomes. A head will occur when flipping a single coin. So our outcome here is just heads, and your homework is actually just going to ask you to write it out in brackets, basically as your sample space. What's in your sample space here is just heads, because it's not heads and tails, because you're just flipping the coin and you got heads to happen. So the key is just writing out what happened in your sample space. Okay. So we've got 2 girls and 1 boy are born into a family. Well, you're only going to have the 2 girls and the 1 boy, but then we've got order in which you can actually have them. So our sample space is going to be boy, girl, girl, girl. We could do girl, boy, girl, or girl, girl, boy. But this is your size of the family, and that is your sample space. It's talking about arrangement, so it does matter what the birth order is here. And then you've got a total of 5 occurs when you roll a pair of dice. And so this goes back to earlier in the last lesson where you actually have where 5 comes up, and then that was just listing, these are all the different ways to get a 5 from the table. So we've got 1, 4, 2, 3, 3, 2, 4, 1. Those are the different ways that you can roll a 5 with a pair of dice. And that's actually from a previous problem that I showed. So now probability, the intuitive meaning of probability. You'll have decimals or fractions. So you might see 0.5 as 1/2 or half chance of something happening. 1.0 is 100%, or 1 out of 1. Okay, so you also see 0.5 as 50% chance. Okay, so 50-50 chance of occurring. Anything over here is likely to occur, and then a 1.0 is absolutely certain it will happen. And a 0% chance is it is impossible to happen, unless it's 0% chance of rain, because you never know with weather. But anyway, side note. Empirical assignment of probabilities, we've got there's difference between experimental and theoretical. Experimental is just the number of times it actually happens over the number of times that an experiment was performed. In other words, like if I flip a coin 3 times and I get tails, 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 what's the chance that I got tails? Well, it was 3 out of 3 tosses, so it's a 100% chance that I got tails. So I know that that's weird because you're like, well, it's 50-50. You should be getting 50. Yes, it is. But out of the experiment itself, this is just the experiment, I had tails, tails, tails. So what's the chance that I got tails? It's 3 out of 3 chances. So that's what this particular formula is talking about here. So here we've got a sample of 100,000 firstborn babies. 6 were found to have a certain syndrome. So what's the empirical probability? Now when it says empirical, that's the same thing as experimental. The probability that a family's first child will be born with this syndrome. And so we've got, based on what our experiment is or what we've seen happen, we just take our 6 and divide it by 100,000. And to get the actual probability, you divide that. Oops, sorry. And we get 6 divided by 100,000. And that should give us a very small number. In fact, my calculator turned it into a scientific notation. 1, 2, 3, 4, 6. 1, 2, 3, 4, 5. This is the probability that this family's first child will be born with this particular syndrome. So again, you just take what actually happened and take the amount that it actually occurred divided by the total possible here. Okay. So now we've got pharmaceutical companies testing a new flu vaccine. So down here the question is, if the physician injects a patient with this vaccine, what's the probability that the patient will develop severe side effects? So severe was 3 out of the total. Well, there's only 100 times, so it's 3 out of the total 100 that we divide it by. So it's 3 occurrences, and then out of the total 100 people that we tried it on, and so it's just 3 divided by 100, which is 0.03% chance, or not percent, but 0.03, which is 3% chance of this actually occurring. Now, what I did here was I moved the decimal place 2 places over to get my percentage. And by this, my calculator gets the decimal, move the decimal 2 places, and that gives me my percentage. I don't think I talked about it on the last slide. Here, if I move this over 2 places, it's 0.006% chance of actually getting that to occur. Okay, so here we go. We've got marital status of men and women between the ages of 18 and 34. So it says all the numbers represented are in thousands. If we randomly pick a male, what is the probability that he is married but not separated? Okay, and I think I've got some things to click through here. So we've got, we want to recognize that only the line marked males, which is highlighted here, is highlighted in the table, because that's all that's relevant to the whole question. So in other words, we don't actually care about the females on the whole chart. So our sample space is just the males here. The total size of the sample space is the 36,052. Okay, so what we are worried about is which ones of these are married but not separated. So we take our 9,740 and divide it by this total number, and that will give us the chance of selecting a male that is married but not separated. Okay, I don't know why it says except separated and up here and over here it says not separated, but that's the way it came in the textbook. Anyway, so 9,240, or 7, sorry, not 2, 7, I looked like I wrote a 2, divided by 36,000, uh, 52, should give me 0.2701, or just 27% chance that you would select a male who is married and not separated. So it does say here that you are picking a male, and so if it just said specifically a male that is now married out of the whole table, then we would have to have the total of everything. But it did say if we randomly pick a male, what's the chance that he is married? So it limits the table size. So be paying attention to the way that the questions read as you're working through these problems here. So now we get into theoretical probability, which is more what we think of when we think of probability. When you say, you know, what's probability of getting heads, you would say you've got heads out of heads or tails. So in other words, it's 1 out of 2 options, so it's half chance of getting heads. So this is more theoretical. It's just a general probability of kind of more what we think about rather than what we've done so far as experimental. So what's probability in a family with 3 children that 2 of the children are girls? Okay, well, to answer this question, you have to say, all right, well, you could have 3 boys. And this, by the way, is coming from the first page. You could have two boys and a girl. You could have 2 boys and a girl this way. You could have a boy and 2 girls this way. So there's all these different ways that the family could come out. So the question is that 2 of the children are girls, so we want to select all the ones that have 2 girls. And then we can include this last one here to have 3 girls, because I would still have 2 of the children are girls. So it looks like out of the 1, 2, 3, 4, 5, 6, 7, 8 different ways that we could do this, there are 1, 2, 3, 4 ways to select a girl. And so here, oops, I guess we're not including the last one, 3, I'm sorry. That one's got 3 girls, not 2, sorry. We put that over the 3. And so we take the number of ways to get 2 girls, which is 3, and divide it by the 8. And so it's 3 out of 8 different ways that we can do that. This is why I give myself notes that come in, because I overthink something. So in other words, this last guy right here, it's got 3 girls, and it specified that 2 of the children are girls. Didn't say 2 or more. I apologize for my earlier what I said. Anyway, so 3 out of 8 is what we're looking at here. Okay. So what's probably that the total of 4 shows up when we roll a fair dice? Well, this is nice that we have this table that came up earlier, and that is where we sum up to be 4 is right here listed for us. And all of these are listed. You'll have some questions like this in your homework, so it would be nice to take a picture of that. And there are 3 ways to get a 4, and these are the 3 different ways that you get a 4. And there are 36 different ways to roll the dice, so the answer is 3 out of 36. That's it. And if you reduce, of course, you get 1/12. There we go. We've got draw a 5-card hand from a standard 52-card deck. What's the chances that all 5 cards are hearts? Well, this one's a little bit harder. Here we have to actually do a combination, because to get the total sample space size, we would do a combination of 52 and 5 from our last chapter. And then to have all of them be hearts, well, there's only 1/13 of them that are actually hearts. And so we would want all 13 or all 5 of them to be hearts. So we'd want to choose out of the 13 hearts, we would want to be choosing 5 of them. And if you're not familiar with your cards, maybe do a little side research on cards. There's 13 different cards in each suit. The suits are hearts, spades, clubs, and diamonds. And anyway, we want hearts specifically here. So we've got these 2 different combinations happening. We don't care what order they happen in. We've got this is dealing with the hearts, and this is the overall sample space. So our job is to actually divide this answer by the overall size of the sample space. And I think I do that in my slide here, which you can see that behind there, is if you do the top one, you get 1,287, and the bottom one is 2,598. And if you divide them This is the probability. If you move the decimal place over 2 places, it's 0.05, basically, percent chance of having them all hearts. Okay? So you've got Leonard, Sheldon, Penny, and Raj belonging to the Greens, their school's 10-person environmental club. 2 people from the club will be selected randomly to attend a conference in the Everglades. What is the probability that 2 of these 4 friends will be selected? Well, what we want to do is take out of the total, there's 4 friends, and we're wanting to group 2 of them. We don't care what order, so it's combination. Divided by the combination of out of the 10 people we're selecting, 2 people from the club will be selected randomly, so we got 2 people total. So out of these 2, how many ways can you group it? Out of the overall ways that you can group 2 from the whole club. So if you do that on your calculator, this is explaining what I'm saying, if you want to read that. Bottom line, you do this, which is what I just had written, and the first answer, if you do it on the calculator, you're going to get 6. The second answer is going to get 45. Then you reduce it, you get 2 out of 15, which is 2 divided by 15, 0.133, and basically a 13% chance that you might have 2 of the friends get selected to go on that trip. All right, so you got a anemia type question. It's not anemia, it's a different disease in the homework, but you've got to understand this table to answer that question as well. So this is saying that you've got something 30 times more likely to occur in African American babies than non-African American babies. And a person with 2 sickle cell genes will have the disease, but a person with only 1 sickle cell gene will be a carrier, but won't actually have it. 2 parents who are carriers of the sickle cell anemia have a child. What's the chance of the following? The child will have anemia. Well, the only way to have it is this guy right here, which is both the parents have it. You get both the genes, so it's 1 out of 4 different outcomes. So this is 1 out of 4. So the child is a carrier. Okay, well, carrier here, so that's 2 out of the 4 is a half chance that you will be a carrier. And then the child is disease-free. Well, that's the same as getting a disease, which is 1 out of 4. So that is how you work the table there. A very similar situation in your homework. Okay, so we've got a definition for odds against an event are simply the number of outcomes that are against E, the event, compared with the number of outcomes in favor of E occurring. We would write these odds as number of E prime, which is the complement of the event. And this is going way back to section 2.3. And so here we take the complement of the event and divide it by how many, the probability of the event's complement, dividing it by the original probability of the actual event. So let's take a look here. Safest place to be seated in the event of an airplane crash is in the aisle seat above the wings. I didn't know that, so that's good news. I think, especially on different flights where you can actually seat yourself. In this case, the probability of surviving a crash is 56% chance. That actually sounds pretty good about surviving a plane crash. But what are the odds against you surviving? So that's actually a more morbid look at it, but what are the odds against you surviving? So to do this, we have to actually think about it this way. We've got 56 is the probability of you actually surviving. So 44 is the probability against you surviving. So this is saying we take our probability, 0.44, and divide it by our 0.56. And then that'll actually give us our odds against me surviving. So here, if I actually do this, 0.44 divided by the 0.56, I get 0.786. So that's actually a 78.6% chance. It's the odds against me surviving. Not very good odds. We're going to be surviving our plane crash. And this is working out what I just did. So 11 to 14, by the way. Anyway, so suppose that 4 cards are drawn from a well-shuffled deck of 52 cards. What's the probability that all 4 are clubs? So, again, this is very similar to the problem that I did earlier. It's actually identical. But here, clubs, there's 13 clubs, and we're selecting 4 of them. And this is a combination because we don't care about order. And then here we've got 52 cards, so we divide it by the 52 card deck. but we're choosing 4 cards, combination there. And I think I have it set up here, so this is exactly what we're doing. And then if we actually do it on our calculator, we have 13 NCR4 divided by 52 NCR4. So that's 715 divided by 270725. So if I divide that, 715 divided by 270725 gives me 0.0026, which is, if I move it over 2 places, 0.26% chance of that actually happening. Very small. So a cookie selected at random from a basket containing 24 mint cookies, 16 caramel, 14 peanut butter, and 6 sugar. What's the probability that a mint cookie is selected? So to do this, you take your desired, so this is just desired, the formula, over the total in the sample space. Okay, so desired number we'll say. So here we've got 24 mint over the total, which is 24 plus 16 plus 14 plus 6, which is 60. So the chances of getting a mint cookie is 24 out of 60. So if I take my 24 divided by the 60, I get a 0.4. In other words, a 40% chance of actually getting my mint cookie. And that's it for this section. If you have any more problem-specific questions, you can email me through the Ask